make you interested like me, but I'll try to explain that it's a decent thing to do, and yeah. So today the time is limited, so I'll focus on how string theory motivates models. So it will be review and some case study. But as a whole program, we would also like to make a prediction of the model to observations. And for that, there is a work by Vignesh sitting there, a poster. So please ask him about this part. And after making model predictions to observations, you would like to test with cosmological data. And for that, later you will hear about that from Sweden, former PhD student, and right now NPDF at IIA with Pravar, and Kanan, Pravar's student, also working on this part. And so I think previously some of the researchers were motivated by swampland. That is encouraging. So this is about the universe, and you have seen many times. And I'm just showing this to motivate particle physics model of inflation. So universe started as such a high energy and density. We need elementary particle physics to describe it. So that introduces us to think about what is particle physics. So particle physics is described by quantum field theory. And basically everything is measured by energy scale. Length is inverse of the energy, momentum is energy unit, etc. So we talk about energy. High energy means higher energy means shorter distance, right? And current standard model of particle physics can describe around 10 to the 3 GeV or so, giga-electron volt. And there are theoretical reasons that we expect it to be modified a little bit above that. And above that, we have scarce data to know what is particle physics describing this higher energy. And simply extrapolating, the quantum gravity is expected to be relevant at around 10 to the 18 or 19 GeV. I'm using so-called reduced Planck's mass, which is a little bit smaller than the standard Planck mass and which is more convenient for particle physics. So so there's a huge gap between this quantum gravity scale and the scale we currently understand. So to guess what is happening here is really, really challenging thing. And so how to know the physics, particle physics beyond the standard model? One is top down. So assuming the fundamental principle and trying to define the theory at the shortest fundamental scale and trying to make a prediction. And of course, so it's really hard way. And another approach is bottom up, which is more modest. So you know this part, and based on the knowledge you have, you try to do from the lower energy. And so yesterday we heard about effective field theory. So effective field theory is a suitable framework for bottom up because effective field theory is a theory limitation. So it has a highest energy cutoff, UV cutoff. So above which this theory is known to break down, and that's fine. This theory can describe anything below this cutoff scale. This arbitrary good precision you want. So basically, effective field theory is a power physics expansion in terms of E over cutoff scale, where E is the energy of your interest. And the energy of your interest is always below cutoff scale. So yeah, this term will go smaller and smaller as n integer n becomes larger. And this can also be used to discuss whether some parameter values are natural or not. And so for given particle contents and symmetry, we write down all possible terms in the action. So you can see this is the most general framework to describe the physics below lambda UV cutoff. And the foundational theorem for effective field theory is this decoupling theorem. This is basically saying, so if there's a theory which describes the higher energy scale, more fundamental theory, even though it exists, their effect at low energy is only to shift parameters of the low energy effective field theory. So that means if parameters are fixed experimentally, you don't need to calculate it from fundamental theory. So you really don't need UV theory. Yeah, so yeah, if you know the particle contents and symmetry, this is all you need to describe elementary particle physics below lambda UV. And so yeah, effective C theory is such a nice framework. So you see a lot of people who really love it. So during the COVID time, for example, those people were having online meeting, and you can see they really love this effective field theory. And I think many of them have this kind of view. So at some energy scale, you have effective field theory 1, which can describe the physics below lambda 1. So above that, what will happen? So above that, there's another effective field theory 2, which can describe the physics at this energy scale. And that will also break down at some energy scale. And then it goes on, goes on, goes on. You can continue almost forever. Well, even then, actually, Planck scale is a little bit special. So quantum gravity is a little bit special, and probably effective C theory cannot be used above quantum gravity scale. So now I change the direction. So now the top-down approach. So top-down approach, so now I replace quantum gravity with string theory, which is the most promising candidate for the unifying theory of all the forces in nature, including quantum gravity, consistently. And we have a typical energy scale, or length scale, or 1 over string scale is energy scale. And so you try to make prediction. Or you can observe. So now let me explain some relevant elements of string theory with this one slide. So in string theory, different particles come from different oscillation modes of the same string. So this is the unification. All the particles in nature coming from single string. And also, importantly, those particles comes as a set. So you start from string theory. You cannot choose, I want this particle, but I don't want this particle. No, if it is in the string oscillation, you have to have all of these. That's one important feature of string theory. And for theoretical consistency, it predicts 1 time dimension and 9 space dimensions. But the world we observe is only 1 time dimension and 3 space dimensions. So there are 6 extra dimensions. So those are supposed to be compactified, meaning you cannot resolve it in the current experimental method. And low energy, they are roughly reduced to supergravity or super Yamil. Here, super has a special meaning, not just super means a symmetry which extends boson and fermions. So, but string theory can also have extended objects, such as plane, D-plane, or plane, etc. So these are specially extended objects. build your low energy model. And also, field theory doesn't have any tunable parameters. Parameters of low energy effective field theories are dynamical fields that take some constant values at low energy. And I'd like to mention that theory is not complete. The situation is a bit like old quantum mechanics. You have some theoretical framework in the old time, but we still don't have modern version of quantum mechanics. So we can do something, but something we can't do. But with some controlled approximation, researchers have found that string theory has a lot of minima of the potential energy. So 5,152 are scalar fields. String theory can have a lot of them. And the potential energy is described like that. So it looks a little bit like a mountain. So that's why it's called landscape. And bottom, so if you can excite only the low energy, the bottom is described by, and yeah, depending on the parameter value of phi1 and phi2, the parameters or even the field contents in each vacuum are different in different theories. So this landscape of string theory vacuum motivated people to think that any effective field theories may be embedded in string theory. But then, around 20 years ago, Buffer came with caution that no, not all effective field theories can be consistent with quantum gravity. So he called the space of effective field theories inconsistent with quantum gravity swampland. And swampland conjectures are proposed criteria for rejecting effective field theory in the swampland. So this is like a top-down constraint on the bottom-up effective field theory approach. And it's a little bit against the effective field theory philosophy of that. So the questions like that of string theory. So usually effective field theory thinks you don't really need to know so much about high energy theory. But the swampland conjecture claim that they can actually secretly constrain the effective field theory at natural energy. Well, actually that's what they want to do. So this is the space of effective field theories. So if you distinguish the effective field theories with different parameter values, then the space is continuous, and so this each point in the C space represents one effective field theory. But so swampland conjecture will kill like the effective field theories in this region. It is proposing it's not consistent with quantum gravity. And then there are several conjectures so far proposed. So this conjecture will kill this region, and this conjecture will kill this region, and we end up with very tiny consistent theory. That's the idea. So let me look at one example of swampland conjecture. So one is distance conjecture. So this distance refers to the distance scalar field space. So as scalar field go close to Planck scale, cover of light appears with some energy scale which decreases exponentially with phi, which is some order 1 constant. And this happens, so cover of light space is space parameterized by integers. So like oscillation is quite common. So this is the new particles are coming into the effective theory. That means original field theory breaks down. And the more defined version of this one, the critical version of this one is emergent string conjecture. So this conjecture proposes that this tower is either a Karuza-Kram-Morse coming from the external momentum or fundamental string oscillation. It has integer oscillations labeled by integer. Another conjecture is weak gravity conjecture. This basically proposes that the gravity is the weakest force in nature. So when compared with gauge force, so charge must be bigger than the mass in Planck unit. So that is a proposal, and this makes effective field theory with small gauge coupling difficult. And if you consider Dirac magnetic monopoles and magnetic force, it we'll get this condition for the UV cutoff scale. And this also makes small e hard. If you make e small, the cutoff of your theory is becoming down and down. Your applicability is more and more restricted. Then there's a proposal that this weak gravity conjecture and the sun conjecture is connected. So if this UV cutoff goes down as you take E small, so it is identified with the sun conjecture, tower of light states appears. Okay, so then, okay, so this is a little bit critical view on swampland conjecture, and this is my personal view and also very qualitative view. But what I want to say is there are many swampland conjectures, and their plausibility and usefulness differ. For example, yeah, we have had this Rosetta swampland conjecture or trans-Planckian censorship conjecture. These constrain effective field theory very strongly. But in my personal opinion, the theoretical basis that this comes from string theory is quite weak. So plausibility is actually quite low. On the other hand, distance conjecture and weak gravity conjecture, it's quite plausible. String theory has a lot of examples of these. However, what they are constraining may not be effective field theories, but something else. So the situation is like that. So originally, swampland conjecture tried to constrain this, but some of them only constrain the energy scale just below the string theory. Or something constraining effective field theory actually may not come from string theory. That is, I think, what they actually end up with at the moment. But people are trying to make some swampland conjecture more plausible. And the method is to use, try to find more and more examples in string theory vacua. You cannot prove by this way, but it becomes more and more convincing. Or also, zero, okay. So black hole is always a good testing ground for quantum gravity. You do some sort of experiments and see whether it's reasonable. Okay. Okay. So then, I have some work. So another question you can ask is if you have effective field theory which is constrained by swampland conjecture, whether this constraint will propagate into the lower energy to constrain. And to make long story short, so its situation is like this, and in this case, it turned out that so if this theory respect weak gravity conjecture, this theory also respect weak gravity conjecture. That's what we showed. And okay, I think I have. Okay, but this is the last slide, maybe. So then we also try to check weak gravity conjecture equals to distance conjecture. And so I skipped all this explanation, but so we propose extended proposal for string swampland conjecture, and that is crucial for describing some inflation model using effective field theory framework. And so summary, so I try to explain string theory to effective field theory via swampland proposal. And most of the conjectures still remain conjectures. And as I said, they might not constrain effective field theory contrary to the original purpose. And we made a case study for those constraints propagate to low energy or not. And in this study, we assumed the starting point, the swampland conjecture was expected, but it is interesting to check it in explicit string theory example. And I like to caution that so this is my views and may not be shared with many of my colleagues, but I'm trying to claim that I am correct. Okay, thank you.